Welcome everybody for this defense of my habilitation, which is entitled Towards Language-Oriented Modeling. And thank you very much for attending this presentation. Thanks especially to all of my jury members. I'm very glad to have all of you physically here in Rennes, giving me the opportunity to present you an overview of my research work during now the last decade since my PhD thesis. So let's start by some details about the application context. So as a software engineer, I'm mainly interested into complex software-intensive systems that range from safety-critical embedded systems to system of systems, distributed systems, and all the new kind of smart technologies ranging from Internet of Things to cyber-physical systems. And in all those complex systems, I'm mainly interested into a very fixed set of properties. The fact that all of them are developed using a multi-engineering approach, which involves different stakeholders while developing the system, and where all the different stakeholders are coming with different forms of domain-specific modeling, and where software is more and more used as an integration layer of these different engineerings, physics, electronic, mechanics, and so on, and where software is also used for reacting to a more and more open and dynamic environment in order to adapt the services provided by the system. So we looked at these different complex systems and these different properties with different actors from industries. That was really important for us. So first of all for funding the research work, but also for providing real-world case studies that let us the opportunity to keep our research work grounded into industrial problems, and which eventually experimented and evaluated some research results on those case studies. So if we are zooming on one of them, this is a cockpit of the Airbus 380, and if we are looking on how such kind of systems are developed, of course, there is many different concerns to consider while developing those systems. And for addressing these different concerns, there is different stakeholders, very different stakeholders with different background, different expertise, different experiences, and using different tools and methods for addressing the different concerns. And if we are looking at the different tools and methods that these different concerns are, different stakeholders are using, we can see that they are all using models. They are all using models, but very different domain-specific models that are tailored in order to better address the different concerns to consider while developing those systems. So there is at least two underlying main challenges of this situation. The first one is to be able to build these different heterogeneous models, which means that we need the different domain-specific modeling formalisms in order to define those models. And the second one is to be able to coordinate these different heterogeneous models in order to reason over the entire system, to be able, for example, to check some global properties on the system. So we just recently had some evidence of this use of domain-specific models, for example, with one study conducted by some colleagues in UK, especially John Whitted, that started a project in 2009, finished in 2011, and where one of the key findings of this study was the fact that the majority of the model-driven engineering examples in their study followed domain-specific modeling paradigms. So this use of domain-specific models has a big impact into the development process employed in industry, and especially the fact that the development process is broken down in two, with one language engineering process whose the main objective is to build the domain-specific modeling languages to be later used by the system engineers in order to build the final application. And when we are talking about the domain-specific modeling language, we are talking about the language itself, which means a set of constructs with their specific meanings, but also about all the toolings around this language. First of all, the editors, whatever these editors are graphical or textual, in order to be able to build the conforming models. But also validation and verification tools in order to be able to check as early as possible the different models in the development process. And eventually some generators for documentation, test cases, or the code itself. So for developing these tools, software languages are software too, which means that we need to define a proper engineering for addressing the different activities required for developing software languages. And the community came out with a new engineering, which is a software language engineering, which is defined as the application of systematic, disciplined, and measurable approaches for the whole life cycle of a software language, which means the development, deployment, use, and maintenance of these software languages. And for supporting this new engineering, we have dedicated IDE dedicated to the development of software languages, which are called language workbenches. And we have now different kind of language workbenches, for example, the Eclipse modeling framework and all the different tools around this framework in order to build the different concerns of a software language. But also MPS proposed by JetBrains or DSL tools, which is now directly included into Visual Studio by Microsoft. And using these language workbenches, we can implement software languages in a different way with different shapes. We can talk about external, internal, or embedded DSL, or even profile, which is a very specific way to do internal DSL in UML. And we can use different technological spaces, such as grammars, metamodels, ontology, and so on. And more recently, we even have more and more literature. So we have seen in the last 5 years many books about software language engineering and the development of domain-specific languages. And we have even a dedicated international conference, which is called ACM, and which is now sponsored by ACM, and the first edition was in 2008. So there is scientific context of my research work in between model-driven engineering and software language engineering, trying to propose some approaches on metamodeling. And the main objective was to leverage on knowledge coming from the application context in terms of domain modeling, to be integrated into software languages, to be eventually used as domain-specific modeling languages for defining the different concerns of a given software-intensive systems. And we did it with a very strong focus about early dynamic validation and verification, which means that our focus was to support as early as possible the possibility to check some behavioral properties on our models, which means that we need to provide executable modeling languages in order to be able to execute the conforming models. So the key challenge that we tried to address during the last decade is first the development of executable domain-specific modeling languages, which means that we try to consider different domain knowledge to be integrated into the specific concerns for implementing software languages, to be supported by generic and generative approaches for automating as much as possible the development of dynamic validation and verification tools. So we did it by defining a pattern that we called XDSML for executable domain-specific modeling language in order to try to modularize as much as possible the definition of XDSML and to support it by generic and generative approaches. And we did it with different students. First of all, of course, Erwan Booth that defended his PhD thesis yesterday morning, but also Thomas de Geul that I don't directly supervise, but who is working in the team on those topics. And other PhD students with who I work with, such as Munira and Florent from the University of Toulouse. So then the second challenge is facing the multiplication of executable domain-specific modeling languages. Multiplication due to two facts. The first one is that we are more and more application domains that use domain-specific modeling languages, and we need to be able to reuse as much as possible modeling languages defined in one application domain into the other application domains. And also because we have more and more stakeholders involved into the development of complex systems, and we need at some point to coordinate the different languages used by these different stakeholders. So for this, we worked on different language interfaces in order to support some different composition operators for addressing this need for reuse and coordination. So we first defined a structural and axiomatic language interface, which is supported by structural composition operators that support the reuse of modeling languages. And we also defined a behavioral language interface, which is supported by behavioral composition operator in order to coordinate at runtime the different conforming models. And we did it with different students, especially Clément Guy, Emmanuel Rouillet, and David Mendes, that I supervised in the team. But also Matthias from the University of Nice, Peter from Colorado State University in the context of a collaboration with Robert France, and a postdoctoral researcher, Jose, which is in the room and which is actually working on those topics. So this is the big picture of, it's at least one slide for 10 years of work. And now I will try to detail a little bit this approach. I will mainly focus on this part, and then I will give you a very brief overview of this part. So let's start by the tool-supported approach that we propose for executable metamodeling on top of the XDSML pattern. So this pattern originally was initiated during my PhD thesis, and the main objective of this pattern was to modularize as much as possible the definition of a language to make this language executable. What we mean by executable is to support the execution of the conforming models. So we started by the domain definition metamodel, which is actually a structural model of the domains that we want to reify in terms of a software language, and which is a graph of concepts and relationship between them, possibly completed by context conditions that are also known as static semantics. And then on top of this domain model, we need to define the behavioral semantics, which is defined in three parts. The first one is the definition of the state definition metamodel, which is actually the dynamic information that will capture the state of the model during their execution. And then we define the event definition metamodel, which defines the different events that will drive the execution of a model from one state to another one, whatever these events are internal due to the data or control flow induced by the implementation of the behavioral semantics. So for example, if you are using a visitor for implementing the behavioral semantics, we can consider the method call as the internal events. Or these events can be also external in order to simulate the stimuli coming from the environment. And once we have defined the events and the states, we can define the execution function, which reacts to the different events that we have defined here in order to change the value of the dynamic information which are defined there. And now we have the behavioral semantics. The main objective was to support dynamic validation and verification tools, which means that we need to be able to capture a complete execution of a given model. So that's why we define the trace management metamodel, which is actually a way to capture a particular execution trace of a given model in order to be able to reason over it for checking some behavioral properties. So that's the XDSML pattern that we try then to support by different tool-supported contributions. The first one was to select a set of meta-languages dedicated to the implementation of the different parts according to their nature. So we use mainly eCore for defining the structural part, which is possibly completed by context condition defined with OCL. And we use Kermeta, which is on top of Xten, which is on top of Java, in order to define the execution functions. And then we can rely on the modularity provided by this pattern in order to provide some validation and verification tools. So for example, we can make more efficient the OCL checking by slicing the input and the input model and meta models according to the footprint of a given OCL property, which make more efficient the checking of an OCL property without changing anything to the OCL checker itself. We can also provide some generative approaches, such as the one proposed by Erwan Booth in his PhD thesis, in order to generate automatically an efficient trace management metamodel, efficient in terms of processing time and memory usage. And once we have this efficient trace management metamodel, we can provide generic facilities, such as generic model debugging facilities on top of this trace management metamodel. And if we are defining the execution function in a translational way by translating the model into a targeted domain, we need at some point to trace back the execution results of the targeted domain in terms of the initial domain, and we define some formal algorithm in order to trace back this execution according to a biosimulation relationship. So this is one example of result. So here we can see a running model conforming to activity diagram. So here is a model under execution. We can see in the stack trace the application of the different execution functions. We can see in the variable view the different dynamic information and the value of this dynamic information during the execution. We can even define some breakpoints on the model, which are defined here and here. And we also have a timeline that we can interact with. So the first line is the entire execution trace based on the trace management meta model. And the other one corresponds to one line per dynamic information in order to follow the changes into a given dynamic information. And on this timeline, we can see, of course, forward the execution of the model, but we can also go backward in order to restore a previous state to explore the execution of a particular model. So of course we can apply this pattern on any kind of modeling languages. So here is another example of a modeling language in order to define sketches on top of an Arduino. So we can define the different actuators and sensors connected to the Arduino, and then we can define the sketch to be eventually executed on this Arduino. So what we can see here is that we can have a graphical animation of this, we can define some breakpoints, we can have a multidimensional and efficient trace management, we have model debugging facilities, and here we can see the real benefits of having modeling languages, because we can verify the proper concepts in order to define on a higher level of abstraction the sketches to be executed on the Arduino, higher level of abstraction than the eventually C code that will be actually executed into the board. And we can even debug this model independently to a given board without compiling, deploying into the board. However, there's still a very key concern regarding the execution of those models. The fact that complex systems are highly concurrent systems, because we have many different entities communicating each other, and we need to take into account the concurrency constraint between them. And eventually we will deploy, allocate this complex system into modern platforms that provide more and more parallelism, whether we are talking about many core, GPU, or distributed platforms. And most of the time, a key concern that we want to verify into our modeling languages in order to take into account some knowledge from the domain is the notion of concurrency. So some construct into our modeling language which is dedicated to manipulating the concurrency of the system and the deployment of on modern platforms. So which means that we want to be able to simulate and to formally analyze the concurrency constraint coming from the system and the deployment of the system. So for this, the main limitation for now is the fact that the concurrency constraints are mainly implicit in the meta language that we are using for implementing the behavioral semantics. In our case, we are using care meta, which is on top of Xten, which is on top of Java, and eventually we are inheriting from the concurrency model of Java. So of course we can tweak it. We can tweak it with the thread API, which is a very low-level API on which that will be very difficult to reason. And at the implementation model, at the implementation level, the concurrency model is mainly embedded into the underlying execution environment of the meta language that we have used. So in our case, we are mainly relying on the Java virtual machine, and we are thus leveraging on the concurrency model provided by the JVM. So there is many drawbacks from this lack of an explicit and formal concurrency model. The first one is that it's pretty difficult to leverage on the concurrency concern coming from the domain or from the different platform on which we will deploy our complex system. The other one is that it's pretty difficult to have a complete understanding of the behavioral semantics, because part of this semantics which correspond to the concurrency model is implicit and inherited from the meta language. It's almost impossible to define dedicated analysis techniques for those concurrency constraints, because the concurrency model is not directly available. And that's also very difficult to have some semantic variation points related to this concurrency model, even if many specifications, such as the OMG one, mention explicitly that in these modeling languages we can change one concurrency model by another one. Even if it's written into the specifications, that's just impossible to do actually in practice. And finally, it's pretty difficult to reason about the deployment of the complex system on parallel architecture, because we cannot leverage on the concurrency constraint coming from these architectures. So the main challenge was to try to cross-fertilize algorithm theory, that is used in our meta-languages for implementing the behavioral semantics, and the concurrency theory. And the main challenge is the fact that if algorithm theory is mainly dedicated for manipulating a state, concurrency theory are mainly dedicated to express concurrency constraint between most of the time event-based structures without anything about dealing about the state. This is what Leslie Lamport stated in his Turing lecture this year, mentioning this fact that manipulating a state in the concurrency theory is something very difficult. So that's the challenge that we try to explore, and the initial idea was to try to modularize the definition of the behavioral semantics, so the mapping between the abstract syntax and the semantic domain, and we try to modularize it in the following way. So we define the execution functions that we call domain-specific actions, and in a modular way we define the model of concurrency that will apply the different domain-specific actions. And of course, the main difficulty behind this is the definition of the protocol between these two parts. So in our first contribution in 2012, we mainly focused on trying to understanding what should be defined into the domain specification and what should be defined into the model of concurrency. And then we use a delegation pattern to apply at some point of the concurrency of the model of concurrency some domain specific actions that will modify the model. But of course, the delegation pattern was really limited in order to match some complex situation into the concurrency model. So we extended this approach in 2013 in order to reify a proper concept that we call the domain-specific events, that are actually the events defined into the event definition metamodels that we have seen into the XDSML pattern. And this concept has been reified in order to be able to match some complex situation into the model of concurrency and then to apply the corresponding domain specifications. But of course, there's still one limitation, the fact that according to the application of some domain specification, we need to restrict some situation into the model of concurrency. Just let's imagine the following example. If we have a conditional, the choice between one branch or the other to be executed is depending on the result of the evaluation of the condition. So if the evaluation of the condition is a DSA, we need to take into account the result of this DSA in order to choose one or the other branch to be executed. So for this, in our last contribution this year on this, we continue to use domain-specific events, but not only as a mapping from the model of concurrency to the domain-specific action, but as a real protocol in order to deal with the data resulting from the application of domain specification for restricting some situation into the model of concurrency. So here you can see the patterns that we have just seen, and for defining this different part of an executable domain-specific modeling language, we provided the different dedicated meta-languages. So we define the abstract syntax using eCore. We define the domain specifications which correspond to the definition of the execution function and the execution state using care-meta. We define the model of concurrency, which is defined in terms of events and constraint, causality constraint between these events with MockML, which is actually an extension of language which is called CCSL for clock constraint specification language that has been initially used for defining the UML Marte profile. And we use a combination of GEL and ECL, two meta-languages for defining the domain-specific events. The first one for the feedback from the DSA to the model of concurrency, and ECL for the mapping from the model of concurrency to the DSA. So this has been implemented with, and supported by compilers. So from the definition of these different constants, we can automatically generate the execution function to be applied on a particular model and the execution model that is interpreted by a solver, which is called time square, and which actually infer a scheduler of the application of the different execution functions that will modify the model under execution. So everything has been implemented into its studio, which is called the GMOC Studio, which is actually composed of two workbenches. The first one is a language workbench, where we can define XDSML according to the patterns that I just presented. And once language has been presented, has been implemented with the language workbench, this language is automatically deployed into the modeling workbench, where we can use this executable language in order to build the model and then to execute the model according to the behavioral semantics that we have defined by parameterizing a generic execution engine which is embedded into the modeling workbench. So coming back to our example of the activity diagram, in this activity diagram, if we are zooming, we can see here that we have a fork with two activities which are defined, which are here in parallel. But if we want to give the proper semantic to the fork construct, this fork construct is not saying that these two activities have to be executed in parallel, but this fork is saying that there is no dependencies between these two activities. Which means that we have at least three possibilities for executing this model. The first one is to execute this activity and then this activity, or this activity and then this activity, or both in parallel. And this is exactly what we can define with our model of concurrency. And once the language is deployed into the modeling workbench, this is exactly what we can see here. We have the three possibilities for choosing the next step to be executed on our model, executing one activity, the other, or both in parallel. And of course, we can explore the different executions. So we have a multi-branch timeline where we have one execution, and then we can go back and take another choice and see another execution. And of course, now we have an explicit and modular definition of the concurrency model. We can change one by another. So for example, here for the very same model conforming to an activity diagram, we can have one concurrency model that supports the parallelism. So here we can see that we can have a coffee and talking in parallel, and then when both are done, we can start to work. And here we have a concurrency model that interleave the execution of the two first activities, choosing to first have a coffee and then to talk, and then when both are done, we can start to work. And this can be just by changing the concurrency model of the behavioral semantics. So now we can define XDSML. We can have even different variants of these XDSMLs, but clearly the next challenge is to be able to integrate the different languages that we are defining. And we have multiple domain-specific languages because we have first an increasing number of application domains, which means that we are defining more and more modeling languages in these different application domains, and we want to reuse as much as possible from one application domain to another one. And we have also a multiplication of the languages because we have an increasing number of stakeholders using different modeling languages to be at some point coordinated in order to reason over the entire system to check some global properties. So this is what we call the globalization of modeling languages, and the underlying challenge of the globalization of modeling languages is the following. The fact that domain-specific modeling languages are by definition defined independently to the other domains. That's exactly what we are learning to our students for defining domain-specific modeling languages, to really focus on a domain and forgetting the other one in order to try to identify the right abstraction for this domain. But eventually, we cannot ignore the fact that those DSMLs have to interact one to the others, and thus we need to provide an associated framework in order to regulate those interactions. This is exactly where the metaphor with the world globalization is coming from, the fact that we have different countries that has been developed independently due to their sovereignty, but at some point they was not able to ignore the fact that one country has to interact with the other ones. So this is exactly how we define the globalization of modeling languages. So the fact that we want to support a coordinated use of modeling languages, or saying in another way, we want to use multiple modeling languages to support the coordinated development of diverse aspects of a given system. And this term globalization is coming directly in opposition of unification, because we strongly think that we are in an open world, which means that we cannot today fix the modeling languages used today and in the future. And even if we want to fix a set of languages, we cannot fix the relationships between those languages, because the relationship between these languages are really dependent of the use of these languages. So that's why we think that we need to support a proper globalization in order to support a socio-technical coordination, which means a technical integration of the different artifacts that we are building for developing a complex system, but also a social coordination in order to support the social translucence between the various stakeholders involving into the development of a complex system. So this big challenge is supported currently by a community that we call the GMOC initiative that we founded in 2013, and where one book has just been published this month, resulting from a Dutch seminar that we organized, and the main objective was to fix the scope of the initiative itself. So there is no answer to any question in this book, but there is only many questions trying to clearly fix the scope of this challenge of the globalization. And in this big challenge, our contribution, our approach was to define different language interfaces in order to support different composition operators between languages. So the first one is the structural and axiomatic language interface, which is defined, which is called model type, and to be supported by a structural composition operator such as inheritance, but also relationships such as the subtyping relation, in order to achieve some substitutability between software languages. And a behavioral language interface, which is defined as a symbolic event structure, and which is later used in order to define coordination patterns between these symbolic event structures to support the coordination of the conforming models. So let's start by the first one, which is eventually supported by a tool which is called Melange, and which provides a modular and reusable DSML design and implementation. So we started from this main motivation, the fact that we are defining more and more modeling languages, as you can see in this slide. But even if we are defining more and more modeling languages, most of the time we try to leverage on recurrent paradigms, patterns, and as you can see here, all these languages are all different, but they are all state charts. So they are all state charts, but all with different specificities, probably tailored for better address the different application domains in which they are used. But of course, what we want to do is to be able to reuse as much as possible something that has been implemented into an application domain in order to be reused in another application domain. So that was the main motivation of the introduction of the notion of model type, initially introduced in the PhD thesis of Jim Steele, supervised by Jean-Marc Jezekiel. And was the main objective is to give a typing semantics to metamodel in order to then to support some subtyping relationships that provide substitutability between languages. And we started from this in order to enrich the subtyping relationships by a set of flexible subtyping relationships, improving the possibility of reuse, and also by supporting OCL constraint into those subtyping relationships. However, as we have seen yesterday, context matters, which means that we cannot reuse as is something defined into an application domain for another application domains. And thus we came out with a modular and reusable approach for developing XDSML, which means that we can reuse different pieces of languages, here pieces of abstract syntax and semantics that we can assemble as we want in different languages. So here, for example, we can put this abstract syntax into L1, and this abstract syntax can be inherited into L2, where we can add different other pieces of languages. And then, once we have a language defined, we can extract a model type on top of which we can define different composition operators, such as the inheritance composition operator, but also merge and slice. So everything has been implemented into a tool which is called Melange, where here we can see that we can define, for example, an FSM, where we extract the model type, which is called FSM-MT, and then we can define an executable FSM, which inherits from FSM, which means that this language is also implementing this model type FSM-MT, and thus when we define a transformation on FSM-MT, of course we can apply this transformation on model conforming to FSM, but also to executable FSM. And also we can construct our languages with different operators, such as merge and the slice operators that I was talking about previously. So this is mainly supported by Thomas Degeul, by developing Melange, where he tried to assemble as much as possible in a safe way different pieces of languages, but in an open world where we have different pieces of languages and we try to assemble them together and to check the validity of this assembling. And David has completed this approach by trying to close the world for a very fixed family of languages to be supported by different tools, for example, and then to represent this family by a feature model that can be directly used by the expert domains for customizing their own modeling languages, and then to automatically derive the implementation of the corresponding language. And now the second interface, which is a behavioral one, and which is supported by a tool which is called BCool for behavioral composition operator language. So the main motivation was initially the fact that we have very heterogeneous behavioral models that at some point we want to coordinate all together in order to be able to reason over the entire system and to check some global behavioral properties. So here we have two state charts, we have a data flow model, and we have even a black box model. And of course, if we want to check global behavioral properties, we need to coordinate these different models during their execution in order to emerge the global behavior of the system. And we decided to define this coordination between the different models at the language level in order to be reused for all the conforming models. And for defining this, we actually reused the domain-specific events which correspond to the relevant in terms of the domain observation during the execution of the conforming model. And we use this relevant observation during the execution of the conforming models as a joint point for coordination, which means that we can define coordination pattern between DSC of a language and DSC of the same language in order to support concurrent execution of homogeneous domain-specific models. But we can also define coordination pattern between the DSC of one language and the DSC of another language in order to support concurrent execution of heterogeneous domain-specific models. So this has been implemented by complementing the patterns that we have seen previously, and where we provide BCool as a way to implement coordination, behavioral composition operators, which are composed of matching rule over the DSC, and then coordination rules between these patterns. So this has been implemented into GMOC, where we can define a coordination pattern between executable languages, and these coordination patterns are then used for generating automatically the coordination model between a couple of models, and then by actually supporting the coordination of these two behavioral models during their execution. So this is what we can see here. We have an activity diagram and a state chart, and once we want to start the release coffee activity, we want at the same time, so this is synchronized with the occurrence of an event from the same name, which is release coffee, which means that we leave this state, execute this transition for going into this state. This is exactly what we can see here. When we execute release coffee, there is the release coffee that occurs in the other model, and then we fire the transition. So here we can see the application of the coordination pattern on those two models. Okay, I think I will start to conclude my talk. So, as a conclusion, the main contribution that we tried to provide was to support a language-oriented modeling with the proper tools and methods for implementing, reusing, and coordinating executable domain-specific modeling languages and the associated validation and verification tools. And these investigations led us to the following major breakthrough: the fact that we had to define a tool-supported approach for modularly defined executable domain-specific modeling languages. We also reified the concurrency concern into the definition of behavioral semantics of those languages. And then we explore some different language interfaces in order to support both reuse and behavioral coordinations. And now for the future, what next? I think what I envision for the future is a support, is a use of DSML as a key pivot for socio-technical coordination. And this is exactly why we define the GMOC initiative, which is something really broader than what we did actually during this research work. But the main objective is to use the GMOC initiative as support of this future vision. And one of the key limitations for now for having DSML as a key pivot for the socio-technical coordination is most of the time the rigidity of our domain-specific modeling languages. And one of the key things for the future is to make DSML adaptable, or let's say moldable, as we have seen yesterday. And for this, we already investigated different visions for this, which are just particular cases of this. The first one is to be able to adapt the language according to the language user needs, which means that according to the task to be realized by a particular stakeholder with this modeling language, we need to provide the proper services on top of the language. This is what we call the metamorphic DSML. So this DSMLs that can take different forms according to the user of the DSML for providing the right services to the right stakeholder to address in the right way the task that he has to achieve. So this is something that we have published into a paper at Onward Essay last year. So making adaptable the DSML according to the language user needs, but also according to the runtime environment. And this is actually the context of the PhD thesis of Marcelino, which trying to apply approximate computing into DSML runtimes for design space exploration, runtime adaptation, and security. And last, but definitely not least, models should be inclusive. Models should be inclusive in terms of scientific models, for example, but also in terms of end users, such as policy makers, different communities, or even preferences coming from end users. So this is what we introduce in this vision, where we need to take into account both scientific models and end user models in order to provide more informed decision and a broader engagement of the society into the adaptation loop of the new kind of smart technologies that are around us in a daily basis. And this has been defined in a vision which is mainly dedicated to sustainability. So I think it's a right week to talk about it, which is a week of the COP21. And that's why I will leave you with this quote, which is probably a quote of my most inspiring guy of the moment, and which is probably exactly saying what I will try to do in the future. So I really thank all of you for listening to me during this presentation, and of course I'm really open to answer any questions that you can have on this presentation. Thank you so much.
Okay, thank you for